So my name is like literally, I'm the only one on the internet with that name, which can be a blessing and a curse, depending on who you ask. So thank you so much. I'd like to talk about concurrency, my favorite topic in Ruby. I've been doing Ruby for 17 years, and for a very long time, I felt very short-handed as far as concurrency is concerned, as I'm sure many of you have too. Because why? We have GIL, we have global interpreter lock. So we'll talk about how that's changed, but before we do, quickly, who am I? Thank you for that introduction. I've been basically doing software all my adult life. And I've been doing Ruby since 2007. I've got a bunch of gems written. Not all of them are popular, as per usual. I currently work at academia, and we are hiring. So I will have another slide on it later. And these are my very brief links. I will show them at the end as well. Oh, yeah. So really quickly, I want to kind of step back a little bit and talk about some of the core concepts that are part of the concurrency landscape. So first of all, kind of a necessary understanding of difference between concurrency and parallelism. And we often talk about concurrent things, concurrency, and then what is it really? Well, the truth is that concurrency is actually just a perception of multitasking, but could be real multitasking, could be real parallelization. But the truth is that we don't really specify what kind of concurrency that is. We just mean that it looks like things are happening in parallel, but concurrency doesn't necessarily imply that. Now, parallelism, on the other hand, does imply that things are happening actually in parallel. And so it's when you have multiple tasks running at once, and they can be executed simultaneously on a CPU. And so to kind of clarify this landscape a little bit further, I want to just sort of touch base on what Unix process is. Hopefully, most of you already know what this is. You run a program, the operating system creates a block on memory. It contains program's code, data, set of resources required, file descriptors, and so on. A program, of course, can request more dynamic memory. As it runs, it may have a single thread, or it may have multiple threads inside. So threads within the program typically are units of execution that can flow at the same time as well. There's two different types of threads that people talk about. There's green threads and there's native threads. And we haven't really talked about green threads in a very long time. But when the first Java JVM came out, they had the green threads until version 1.3. What that meant is that JVM actually emulated threads. They didn't really properly schedule threads on operating system schedule. It did it on its own. And then in 1.3, JVM switched to native threads, and lightweight Java processes are now the same as OS threads. And native thread, of course, is the actual unit that CPU can switch to and pass operation to. And that's done at operating system at the kernel level. So it's all about who is scheduling it. So if we're talking about multi-threaded program, let's say we have a single process. Within this process, there could be any number of native kernel threads. And a single Ruby 2 process, I'm talking about version 2 Ruby, always ran on a single logical CPU core, regardless of how many threads you have in there. But threads were useful even in that case, because sometimes we do I/O, and in a typical Rails application, as you're processing web requests, you may be spending half of your time doing Ruby. Maybe it's rendering your HTML or JSON, and half the time potentially talking to your database, your caches, your file system. And that creates this sort of waiting on I/O time that could be used by another thread to perform those CPU operations. So that's why if you run Puma, you're probably running 2 or 3 threads at the minimum, so that you can saturate your CPU. Why is it important to saturate a CPU? Well, you have resources, hardware that you're paying for. If you're not saturating your CPU, if your CPU is not at 70 or 80%, if it's sitting at 20% consistently, maybe on one core, you're overpaying. You're not actually using what you pay for. So what you want is, ideally, if you're paying for a multi-core server, you want to see every core working, hopefully somewhere around 70 or 80% saturation. Otherwise, you're really wasting the hardware. So the other way that we used to deal with multi-core systems is the multiple process model, where you have a single master, like in Puma, and which creates multiple workers. Same with Sidekiq, although in Sidekiq you have to pay for the Enterprise Edition if you want to run multiple, unless you use Sidekiq Pool Ruby gem, which is free, which does exactly the same thing. And so Server Manager, which started workers, processes, even though it does copy and write, which means that unless the code changes in the fork process, it remains shared with the master. It still is a pretty expensive operation compared to threads. And so if it's a long-running process, that's okay. If it's constantly killing processes, that's really not very efficient. A good example of a server that does it really well is Postgres. It does fork a new process for each connection unless it has some that are idle. And that's because Postgres actively uses shared memory really well, shared buffers. But the reason threads are so useful is because while they have a lot of memory that is unique to the thread, they also have a whole bunch of memory, all of that horizontal lines, that are actually shared across all threads. And so overall, you end up using a lot less memory. And context switching in this context is basically when a Unix operating system goes and says, hey, you've been taking too much CPU, I'm going to pause you and pass the baton to the next thread or next process. And sometimes context switching is voluntary. It's when the thread or process says, hey, I did my part, I'm going to pause and let someone else be on CPU. Or involuntary, which is when basically operating system has to terminate or interrupt the process in order for other processes to continue. And you can often observe the number of context switches on an operating system using VMstat or other tools. And if you're seeing that a particular process is causing enormous amount of context switching, that is often a sign that you have too many threads configured. This is just a small diagram to kind of show you the time running from top to bottom, even though the bottom arrow is a little cut. You sort of see how the threads on a single CPU core in Ruby 2 could never really truly run in parallel. They sort of like pass the baton and then they run. But that happens so fast that to us it looks like they're running at the same time. And this is the same kind of concept, except it shows different tasks on the same CPU cores that are not truly executing in parallel, they're executing concurrently. And that is the world pre-Ruby 3.0. So in summary, we had thread.new that started native threads in Ruby, but we knew that it was bound to single CPU core. We also know that scheduling is performed by OS kernel, with some feedback from the programmer via thread.pass. So we can call thread.pass if you wanted to release the control. Now, fiber.new starts a new lightweight fiber within a thread. And the only difference is that we actually have to schedule fibers ourselves, although that has changed lately with the addition of fiber schedulers. But the idea is that while threads sort of end up getting scheduled by OS, with fibers, you kind of have full control. So you can create a fiber that does I/O, yielded to another fiber that does something on CPU, and then yielded back when something comes back on I/O. So it's a little bit more fine-grained. In a nutshell, pre-Ruby 3, to take advantage of multi-core hardware, we had to either run something with multiple workers, multiple processes, run many single CPU Docker containers, and often run both of those with multiple threads in order to take advantage of any time spent in I/O. And it worked. We could saturate multiple cores, but multi-process architecture does require more memory, and it's slower to start. And so real briefly, I want to touch on Moore's Law and why we ended up here. So you probably all heard of Moore's Law. It's about number of transistors growing sort of exponentially together with the speed of the CPU. And that sort of tapered off somewhere, if I'm not mistaken, around 2012s or 15s, and sort of continues to flatten. And so hardware manufacturers went white instead of kind of high-end CPU. We started having 2-core systems, 4-core systems, and now on AWS, you can easily provision a server with 512 CPU hyper-threaded cores. The question is, well, how do you run software that takes advantage of that? And that is what actually spurred all of this crazy creation of new languages like Go and Rust, those languages that have these concurrency paradigms. A single binary can saturate all of the cores in the system. Their concurrency paradigms, like channels, are pretty safe. They're not as susceptible to kind of typical problems with coding threads, with thread safety related issues, and similar problems. So Ruby was unfortunately behind on that front up until Ruby 3.0, when guilds, which were later renamed to Ractors, were created. So yeah, Ruby 3 was a bomb for me personally, and hopefully for everyone. So let's talk about Ractor. What the hell is it? So Ractors are Ruby's answer to actual true parallelism. Each Ractor has its own memory and runs potentially on a different CPU core. They're not bound to global interpreter lock. And the communication with Ractors is possible, but it's only enabled through message passing, which is the only safe way to do it, and is similar how other languages do it. In a sense, sort of Ractors are like services that send and receive messages. The only thing is they live inside your Ruby binary, Ruby process. So it's like a thread but can't share anything, although that's not technically true. And the best part about this is that a single Ruby 3 MRI process with Ractors can finally saturate every core on your system. Now I can mine my crypto, finally, in Ruby. I lied when I said that they can't share anything. Ractors actually can share some objects. They're called shareable objects. And all frozen constants are shareable. Class and modules objects are also shareable. And what that means is that if your application is enormous, and the class and module objects take up a ton of RAM, then running a single process that shares all of that among all the Ractors and then creating Ractors to do something will actually save you quite significant amount of RAM compared to running it in multiple processes. One of the things that I want to see is a version of Puma, for example, that instead of using multiple processes as workers, uses Ractors as workers, because that would obviously be much more efficient and also less memory. So that's pretty much the overview of all the constructs. I'm going to quickly show you some examples. Now, I'm not going to lie, these examples are from a blog post, which I will reference later. I just didn't think that there was a real need to create something other than factorial to indicate high CPU task. We all know what factorial is and how hard it is to calculate. And then this digest function there just sleeps for 1 second, so it's just sort of deliberately slow. And these examples here show basically a benchmark. At the top, sequential factorial. At the bottom, we are forking 4 times. And you can see that the difference between the sequential and process is, about 3x. So even though you would maybe expect 4x because we're studying it 4 times, but in this case, there's probably an overhead. But it's close to 4x. This example here does the same thing in threads. And this is where we see global interpreter lock in action. There's really no difference, even though we're running things in threads, because none of the threads are waiting on I/O. They're not doing anything that can help us distribute this on a single CPU core, and so there's no benefit whatsoever. This example shows you how to use fibers and how fibers sort of allow you to transfer and yield control from one another. At the bottom, you will see what is actually printed when you run this example. I did run it. It's correct. This is not a lie. What this shows is that if you're building a system that's concurrent and you're using threads, this type of code will likely go inside of your thread, where you will be sort of passing the control within that thread from fiber to fiber. But the way I see it is sort of a process is a superset consisting of threads. Each thread may have one or more fibers to provide fine grained control. The other thing that I learned while preparing this talk is that fibers now have schedulers. And so you can actually use the async gem to set scheduler and just schedule work as a block like this. And in this case, they actually also work really well in parallel because obviously we are sleeping for 1 second, which is an I/O operation. The final example here is with Ractors. And Ractors work very much like processes because you basically, there's nothing shared. We're studying Ractors. We're doing it 4 times. So we will saturate 4 CPU in this case. Now, the total numbers here are not exactly 4 to 1, but I'm sure if you run it longer, it'd probably be closer to that. And this right here is a little video that I put together. I'm a big fan of HTOP. There's a bunch of tools nowadays that allow you to look at systems performance. There's glances. There's a bunch of stuff written in Rust. This is HTOP. And the cool thing about HTOP is it shows you every single core on my Mac. There's 16 of them and how busy they are. On the left top, there's an example which uses Ractors. I'm creating as many Ractors as there are cores on that machine, and I'm grabbing that from etc. module and processors. And over there, I'm going to actually run it. So what you should see is once it's running, all of my CPU cores are going to be pretty damn busy. And this was never before possible with a single Ruby process. So I'm pretty excited about that. So here we Control-C that example. And it looks like I cut the video a little too short. But yeah, basically all the cores went down to 0 after that. The last few tidbits, there's a really helpful gem called async, which allows you to do things like this. So you can be creating reactors like that, and you can wrap your block in async method. It also comes with a sync method, which can be swapped out and effectively does it serially, but it works the same way. So that's a pretty useful gem to know. And then another useful gem is pretty oldie. It's called Parallel. If you ever need to start a bunch of stuff in multiple threads or in multiple processes, use Parallelism because the syntax is pretty much the same. I don't know if they support Ractors yet, but I don't see why not. I'm sure they will soon. So in conclusion, when would you want to use which? That's a big question. So I think that processes are best used when you need real complete isolation between tasks, and obviously you want to utilize multiple CPU cores. Threads are great when you need lightweight concurrency within the process, especially for IO-bound tasks when you're talking to database or caches, but be mindful of the GIL and thread safety. Fibers are great for highly cooperative multitasking or when you need to control your scheduling and manage your non-blocking your operations efficiently. And then Ractors, use them when you need to run multiple CPU-bound tasks in parallel across many cores with a single process. And that ensures safe concurrency because there's no shared state, and the results and inputs are passed as arguments and exits. That's pretty much it. And this is a list of references. If anyone wants to read a little bit more on the subjects, take a screenshot of that. These are great posts to read about this a little further. And thank you very much. That's all I have.